Good evening, everyone. It's my great pleasure to open this evening session of the workshop with the talk of John Siegel. And John is currently a postdoc at Penn State, working with Professor Jinchao Xu. He attended graduate school at UCLA, and his PhD is under the direction of Russ Kaflish in 2018. In his thesis, he studied optimization on manifold and its application to electronic structure calculation, for which he won the Pacific Journal of Mathematics Dissertation Prize. Since then, he has been a postdoc at Penn State working on optimization theory and approximation properties of neural networks. And the title of John's talk is Optimal Approximation Rates for Neural Network with cosine and ReLU to the power k activation functions. Please, Jonathan, the floor is all yours.
Thank you, Elena. There is a slight issue, which it says host disabled attendee screen sharing. So, John, I think you have to make me co-host. I'm not sure what happened.
Am I host? Am I host?
No, I think John Harlem. Sorry.
Oh, John Harlem.
John is going.
Okay, wonderful, success. Now you can go ahead.
Jonathan, you're muted.
John, you can go ahead and you can start.
Okay. Okay. So sorry about the issues. Thanks again, Leonid, and I want to thank Jinchao and John for giving me the opportunity to speak here. And I want to thank everyone who's attending for their attention and for attending the conference, which I think has been great so far. So tonight I'm going to be talking about some recent work that I've done with Professor Jinchao Xu at Penn State. And the problem that we were interested in is we wanted to determine the approximation properties of shallow neural networks with ReLU to the k and cosine activation functions. And some of the results that we've obtained have indicated that these already very simple neural networks can attain a remarkably high approximation rates for a certain class of sufficiently smooth functions. So that's what I'll be talking about today, these optimal approximation rates for neural networks with ReLU to the k and cosine activation functions. Okay, so let me begin with some background. So first of all, let's just look at the class of functions that we're interested in here, right? So a shallow neural network is basically just a superposition of ridge functions. Okay, so this is the class of functions that we're going to be looking at, where by ridge function I just mean this sigma of wi dot x plus bi, right? So this is a function which only varies in one direction, right? And its profile is given by this activation function sigma, okay? And the class of functions represented by our shallow neural network is just a superposition of these ridge functions, okay? What we're going to be interested in is this parameter n, or the width of the network. We want to know, how large does n have to be to accurately approximate functions from a certain class, right? Essentially, how many terms do we need in this superposition in order to accurately approximate a given function?
Hi, Jonathan, we cannot see you. Now you are the co-host. I guess you can open a video.
Okay.
No, yeah, no, it's good, yeah.
Okay, sorry. But you can hear me. Everything else is fine, right?
Yeah, everything is great now.
Okay, thank you. So what we're going to be interested in is looking at approximation by this class of functions, which consists of superpositions of these ridge functions. Okay, so let me first talk about some common activation functions. I imagine many of you have seen this before, but so initially in the deep learning literature, this heaviside activation function and this sigmoidal activation function were very popular and were studied fairly intensively. And recently, in deep learning especially, this rectified linear unit has been an extremely popular activation function. So what we're going to be interested in this talk are functions, activation functions sigma, which are a power of ReLU. So ReLU to the k and cosine. And we'll mainly be looking at the cosine activation function as a building block to help us understand approximation by ReLU to the k neural networks. Okay. And so before I go on, I'd also like to point out, so if k is equal to 1, of course, this reduces to the rectified linear unit. But also if k is equal to 0, we interpret ReLU to the 0 to be the heaviside function. Okay. And that makes sense because we want basically the derivative of ReLU to the k to be ReLU, up to a constant ReLU to the k minus 1. Okay, so ReLU to the power of 0 is the heaviside function, and that'll continue throughout this talk. Okay, so let's just begin with a very basic property, which perhaps many of you have seen before. But the question is whether or not this class of functions represented by a shallow neural network, and whether it even really makes sense to use this. By that I mean, mathematically, is this class of functions represented by a shallow neural network dense in, say, CK? So can we approximate arbitrary functions if we don't even care how wide we have to make the network? We don't care about the number of terms that we need. And you can see, of course, that this is going to depend upon the activation function sigma, right? I mean, if sigma, for instance, is constant or linear or something like, or a polynomial, then it's not going to work, right? Because if sigma is a polynomial of degree k, then any function represented by this neural network will also be a polynomial of degree k. And that certainly won't be dense in this space CK. But remarkably, it turns out that that's the only thing that can go wrong. That's the only obstruction. As long as sigma is not a polynomial, then this space of function, or the set of functions represented by a shallow neural network of arbitrary width is actually dense in CK. And so this shows that at least this obstruction doesn't kind of rule out this class of functions. So this is something we definitely need sort of before we move on. But of course, the interesting question and what we're going to consider is how large do we have to take n? So in order to approximate a given function or functions from a given class, how large do we have to make the width? How many terms do we need? Okay. So that's the question we'll get to in a bit. But first, I want to talk a little bit about why we care about shallow ReLU to the k networks. So, for instance, why do we want to consider the activation function ReLU to the power k? And the reason is because of its relationship with the finite element method. And this can be seen as follows. If you look at the function ReLU to the k, right, notice that this is, of course, a piecewise polynomial function, right? It's equal to 0, and then it's equal to a polynomial. And moreover, it's smooth enough at this breakpoint, right? It's smooth enough that it actually is in HK, right? It's even in HK. It's even smoother than that, but it's certainly in HK, actually. So this, of course, means that our ridge functions, sigma of w dot x plus b, are also going to be in HK. And, of course, our superposition of ridge functions, in other words, the function represented by our neural network, is going to be in HK as well. And here, I don't have any domain here, but this can be any bounded domain will work, right? So the function represented by this neural network is certainly going to be an HK of any bounded domain. And it'll also be piecewise polynomial of degree k, of course. So the relationship with finite elements comes because basically this means that your shallow neural network represents a conforming finite element function on some grid, right? So another way of saying that is that finite elements and shallow related decay networks, they both parameterize subsets of the same class of functions. So they both parameterize piecewise polynomial functions. Moreover, these related decay networks are automatically conforming. They're automatically in HK. And for some more information upon the relationship between finite elements and even deep related neural networks, I'd recommend looking at a paper by our collaborator Jinsai on that relationship. Okay, so elaborating on this a little bit more, what we see is that finite element methods and related decay neural networks, they're parameterizing the same set of functions, but there are some important differences, right? The most sort of obvious one is that with the finite element method, you're looking at a fixed grid in the sense that the grid itself doesn't depend upon your degrees of freedom, right? Whereas for related decay neural networks, the grid itself depends upon your degrees of freedom, right? Which are these Wi and Bi. So the grid here depends upon the degrees of freedom. We can call that kind of an adaptive grid, and you can see an example of what such a grid may look like. Whereas for finite element methods, the grid is fixed independently of your degrees of freedom. And this actually means that, this actually allows related decay neural networks to solve an important problem in finite element method, which is, given a grid, it's actually very difficult to construct conforming finite element spaces of high degree. And the advantage of related decay neural networks is that, well, the function represented by this network is automatically in HK, so it's automatically conforming. Okay, and this is one of the reasons we're interested in it. Of course, the cost there is that the grid depends upon your degrees of freedom, but maybe that's not such a big issue. And for more information on this, and also so for more information on this, I would recommend this paper from Professor Xu recently, where he proposes using these networks to solve PDEs, and the resulting method is called the finite neuron method. And these issues are, he goes into them in more detail in that reference. Okay. So let me now summarize some traditional methods for approximating functions, and then later on we'll see how the approximation rates we attain for related decay neural networks compare with these. Okay. So let's start out with finite elements or wavelets, for instance, and say we want to approximate a function f in HS, right, for some s, by finite elements or wavelets. It's well known that the rate of approximation you're going to get is going to be on the order of n to the minus s over d. Okay, where n is the number of degrees of freedom you have. So one of the issues with this, of course, right, is you have this cursive dimensionality, right, where the rate depends very badly on the dimension. In high dimensions, the rate is very, very low. Now, you may say, of course, well, the space HS in high dimensions is actually extremely large, right? So you're really asking too much of your method. That you're asking it to approximate a too general class of functions. So, that's the reason why you have this cursive dimensionality. But even if you say restrict to very large S, right? If you say, well, I'm going to have S scale with the dimension, then the rate you get seems to be dimension independent, and the class of function is also much smaller. But there you still have the issue that in order to actually achieve this S over D rate, you need high degree polynomials of degree at least S minus 1, or you need very smooth wavelets, for instance. So in other words, you need to use very high order methods. And so even if your smoothness scales with the dimension, you don't have, in a sense, a fixed method for every dimension. If that makes sense. So there still is kind of an aspect of this cursive dimensionality, even if you're looking at very smooth functions. Now, next, let's look at another type of method which was invented specifically to overcome the cursive dimensionality, right? The sparse grids method. And here you attain this dimension-independent rate of n to the minus s. Of course, the cost is that you do have to restrict your class of functions significantly, right? This HS mixed norm is a very strong norm, but nonetheless, this is a very nice method. You achieve these dimension-independent approximation rates of course, on a smaller space. But another issue here is this very high power of the logarithm, right? So this shows up in the sparse grids method. In some instances, you can get rid of it, but generally, when using the sparse grids method, you're going to have a very high dimension-dependent power of the logarithm, which is a problem and kind of goes against this overcoming the curse of dimensionality. So keep these methods in mind in what follows, because we're going to compare with these rates again when we look at what happens with ReLU to the K neural networks. Okay, so next let me go through some classical approximation results for shallow neural networks, and then we'll talk about the new results that we've gotten. So the way that we've been introduced to this field is basically through the work of Andrew Barron. And so as a result, the kind of norms that we've been considering are the norms that were introduced by Barron about 30 years ago when he initially studied this problem. So in particular, what we're going to consider in what follows is the spectral Barron norm, which is defined on a set of functions from a bounded set in RD, as follows, right? What you do is you take an extension of your function to the whole space, you take the Fourier transform, and then you look at this weighted L1 norm of the Fourier transform. Okay. And then you take the best possible extension. Right. So this is kind of a strange norm. One way to think about it is if you look at the unit ball of the spectral Barron norm, what you're going to end up with is you're going to end up with convex combinations of a bunch of different frequencies, with a weighting term that decays as the frequency to the minus s. So if you look at these plane waves with weight 1 plus c to the minus s, you take the convex hull of this. That's basically the unit ball of the spectral Barron norm. Okay, so that may help give some intuition on what it is. I'll also mention that, especially if you went to Professor U's talk yesterday, there's another notion of Barron space, and this is actually why we call this the spectral Barron norm and not the Barron norm. There's another notion of Barron space which is, in a sense, more natural than the spectral Barron norm. And I'll just briefly say the way it differs from the spectral Barron norm is instead of taking the convex hull of these frequencies, you actually just take the convex hull of your ridge functions directly. Take the convex hull of sigma of w dot x plus b directly. Okay, but in what follows, we're going to basically focus on the spectral Barron norm for the following reason, and that is that there's this parameter s that we can play with. And in particular, if you look at what this sort of means, this is basically corresponds to is taking some number of derivatives of the function. It's kind of a smoothness parameter, and what we're in particular going to be interested in is, as s increases, how do the approximation rates of these shallow neural networks change? So as you add more smoothness, how quickly do your approximation rates increase? Okay, so but first let me give the classical approximation rates that Barron and Jones got for the spectral Barron space. It turns out that for this particular space, you can get an approximation rate of n to the minus 1/2 via a sampling argument. And this was first done by Jones for the case where your activation function is a cosine, and in this case, s can be 0, so you basically, you don't need any derivatives of your function, right? It's just that Fourier transform has to be in L1. And then by Barron for sigmoidal activation functions, and in this case, you need some additional smoothness, right? So you need to take s equal to 1 in this norm. And more general results were also obtained a couple of years later for more general activation functions. Okay, so these are classical rates in the Barron space. So classical rates of approximation for functions in the Barron space. This Barron space is quite strange, so you may ask, can you also get results in Sobolev spaces? It turns out that you can. These were first obtained by Petrushev in '98, and these results are as follows. So if you have a function f in h d over 2 plus s, right? So you notice that the smoothness for your Sobolev space has to depend upon d. So in a sense, you have to restrict the class of functions in a dimension-dependent way. And we'll talk later on a little bit more about why that's necessary. But if you have smoothness which depends upon the dimension, then you can obtain an approximation rate of n to the minus 1/2 minus s over d. Okay, and what about this s? Well, it turns out there are some restrictions on s. However, for certain activation functions like cosine, we can take s arbitrarily large. Okay, so for the cosine activation function, we can take s as large as we want and get higher and higher rates of approximation if we assume more and more smoothness on the function f to be approximated. However, for ReLU to the k, my activation function is ReLU to the k, then there's a limit to how large I can take s. In particular, I can take it to be at most k plus 1/2. Okay, and in this case, the rate you obtain is given by this. Right, so you see that if the activation function is ReLU to the k, we can improve a little bit on this n to the minus 1/2 in a high order Sobolev space, but not too much. We can't improve too much on it. Okay, this is better than the O of the n to the minus 1/2 result in spectral Barron space. So let me briefly talk about how these results are related. The fundamental inequality here is that, and this can be obtained easily through Cauchy-Schwarz, is that this Barron space Bs is contained in the Sobolev space h d over 2 plus s plus epsilon. Okay, so in a sense, you can think of the Barron space as adding d over 2 derivatives, but not quite actually, because the Barron space is a bit larger. The spectral Barron space is a bit larger because if you look at, for example, single frequencies, as omega goes to infinity, you can see that this is always going to be in Bs, but it's only in H, but it's not going to be in HD over 2 plus S, right? It's only in HS. The idea being essentially that functions in the spectral Barron space, they don't have to be that smooth, but they're only not smooth in a small number of directions, essentially. Okay, and in fact, we have the following embeddings. So one natural thing to ask is, well, we got rates better than n to the minus 1/2 for this high order Sobolev space. Is it possible to get better rates if f is in the spectral Barron space as well? And the answer to that also turns out to be yes. And then this was first observed by Yuli Makovos. And it turns out that he showed that if sigma is a Heaviside function, or in other words, ReLU to the 0, then you could obtain a rate of n to the minus 1/2 minus 1 over 2d. Okay, and similar results have been obtained also by Barron himself and by Professor Xu for higher powers of the ReLU. Once you get to at least ReLU to the power 1, so once k is at least 1, it turns out the rate you can get is n to the minus 1/2 minus 1 over d. Okay, so these are rates that are obtained for single sort of very specific activation functions, like ReLU to a certain power. And one question you could ask, and this is one of the first questions we asked, is, well, can you actually extend these improvements to more general activation functions? And for this problem, we actually did obtain a positive result. So it turns out that even for quite general activation functions, you can still get a little bit of an improvement past n to the minus 1/2. You need to assume some decay conditions on the activation function, and you need to assume a little bit of additional smoothness on your function f, but you can obtain these improved rates for general activation functions as well. However, the improvement you'll note is not very much. It's at most basically 1 over d plus 1, and we're also not really too interested in general activation functions, right? We generally, I mean, we're really interested in those specific ReLU to the k activation functions. So getting results for very general activation functions is nice, but not really the most interesting thing. So the main question that motivated us in this work was, can these rates be improved further, right? So in particular, in Barron space, we see the largest improvement we can really get is minus 1/2 minus 1 over d. which of course in even moderate dimensions is very small. And even in the Sobolev space, right, which is where we've obtained the best, or where Petrushev obtained the best results really so far, for rel u to the k, the best rate we could get there is n to the minus 1/2 minus 2k plus 1 over 2d. Okay, which still, even for moderate dimensions, this is very small. So the question that guided us was basically, well, if we assume more and more smoothness, if we're willing to assume that f is in a very high order spectral Barron space, can we get high order of rates of approximation? Okay. It turns out that the answer to this question is yes. So first, let me state the result for cosine networks. It turns out that if f is in this BS space, then we can get an approximation rate of n to the minus 1/2 minus s over d. Okay, now notice that here we can actually get an arbitrarily high order of approximation as we assume more and more smoothness in this spectral Barron space. And this result is actually very similar to Petrushev's results, if you'll recall, because when the activation function was a cosine, Petrushev could take his s arbitrarily large there as well, but we've obtained it in the spectral Barron space, which is slightly different. So this result is not really too surprising or interesting in its own right, but what's interesting about it is that we can use it to obtain very good rates for the rel u to the k activation functions. So it turns out you can actually, for rel u to the k activation functions, push the rate of convergence all the way to n to the minus k plus 1 with a single logarithmic factor here, right? And notice that here, this is the rate that you would get if you were approximating functions in one dimension with piecewise polynomials of degree k. This is much better than the rate that Petrushev got even in Sobolev space, right? Because this is dimension independent. For any d, we can obtain this rate with rel u to the k neural networks. And it, compared with the finite element method and wavelets, instead of having a minus k plus 1 divided by d, the divided by d is gone, right? So we basically, our rate is a factor of d better, a power of d better than the finite element method. And this is even though we're using a fixed degree polynomial here, right? K is fixed. So we're not looking at higher and higher degree polynomials. We have fixed degree polynomials, and we can still achieve these rates. So in a sense, right, our method does not depend upon the dimension. We don't have to use higher and higher order methods in high dimensions. The method is the same in every dimension, right? The space of functions is the same in every dimension because k is the same, and we can nonetheless achieve these very high rates. And even if we compare with sparse grids, we see that what we've done is we've reduced the power of the logarithm all the way to 1, right? So we get rid of this high power of the logarithm if we compare with sparse grids. Okay, so these results were very surprising to us. And just to be fair, let me say how large you have to take S. Of course, it's going to scale with D. I mean, in a sense, it has to, but you can see it's basically just D plus 1 plus times k plus half, right, plus half. So this is exactly how much smoothness we need to get this rate. So this was very surprising to us. And next, let me illustrate how we were able to get this. Okay, and I'll show how we get the results for cosine networks, and then I'll talk about how we got these results, how we extended that analysis to rel u to the k networks. Okay, so to analyze cosine networks, what we did is we took a closer look at this spectral Barron space, basically. And remember, if a function is in the unit ball of the spectral Barron space, that means it can be written as a convex combination of these plane waves. So a convex combination of these frequencies. Now remember, we're on a bounded domain, right? So we've got these frequencies on a bounded domain. What you can try to do, right, is you can try to cut it off and make it periodic, right? What that'll do is that will force your frequencies to be on a discrete lattice. All right, so notice here in this convex combination, your frequency can be anything in RD. But if you were to cut off cut off the function outside of omega and make it periodic, this would restrict these frequencies to being on a lattice. Now, so that's essentially exactly what we did. You have to be a little bit careful because you want to ensure that your function f still ends up being a convex combination of the resulting frequencies. So in order to ensure that, it turns out you have to potentially shift the grid a little bit. You potentially have to shift this lattice a little bit. Okay, so by using this Fourier analysis argument, we can essentially show that our function f, which is in the unit ball of the spectral Barron space, is actually a convex combination of frequencies that lie on a shifted lattice. It looks something like this. And once you get to this point, a fairly straightforward argument is going to actually work. Namely, what you can do is notice that the frequencies on this lattice are orthogonal, and now we can use a very standard nonlinear approximation method to obtain this result. Okay, to obtain this result where you're basically using the decay on this lattice to get this s minus m over d, this additional s minus m over d factor. Okay, and again, we can obtain arbitrarily high rates of convergence, but again, because our activation function is cosine, this isn't particularly interesting because Petrushev actually obtained the same result. The only difference is that ours is in spectral Barron space. And if you look at this, this is essentially like a spectral method. Okay, what is a bit interesting is that this approximation rate is sharp. And let me kind of explain why that is and how we showed that. And the key idea here is to consider the Kolmogorov entropy. Right? So if you attended Ron DeVore's talk this morning, he also talked at length about the Kolmogorov entropy, but let me briefly introduce it here again. So what we're looking at here is we have some Banach space K in which we're measuring our error, and we have some subset of this space A. Okay, and what we're going to look at is for any epsilon greater than 0, an epsilon net, all that is I'm just covering the set A with a collection of balls. Right, so this B here, sorry, should be an A. So an epsilon net is just a covering of the set A by a bunch of balls of size epsilon. And what I want to look at is how many balls do I need, right? That's this number n epsilon of A is the minimum number of balls you need to cover the set A. The minimum number of epsilon balls you need to cover the set A. Okay, and the logarithm of this is the Kolmogorov entropy. Okay. Now, in a sense, what this quantity measures is it measures the number of bits you need to represent an element of A up to accuracy epsilon. Now, why is that? Well, you know, if you've got these epsilon balls, what you can do is you can just essentially number all of these epsilon balls. That'll describe any element of A up to accuracy epsilon. And the number of those that you get, if you take the log, that tells you the number of bits you would need to sort of count these. So if we look at a couple of sort of simple examples, you know, if A is just a bounded set in some dimension, right, then the number of epsilon balls you need is going to go as epsilon to the minus n, right? So the logarithm, of course, is going to be minus n log epsilon. So this entropy is going to scale with the logarithm of epsilon. Another simple example is if you look at, and here this is the unit ball of the set of Lipschitz functions in the uniform norm, then basically, roughly speaking, in order to identify a function in here, you basically need to describe its value at some lattice, right, or at some set of points that differ by at most epsilon, right? So you need to describe, for example, in 1D, you could take just a grid of points that are spaced epsilon. And so the number of values you need to describe here is going to go as essentially epsilon to the minus d in order to describe a Lipschitz function, right? And more generally, if you look at Holder classes, right, the space C alpha is going to have in dimension d entropy that goes as epsilon to the minus d over alpha, right? And you can see here why the curse of dimensionality occurs. Right, because as your smoothness gets smaller, or as the dimension gets bigger, this entropy is going to be huge. This this means that in high dimensions, these spaces of functions are just very, very large. And in order to come up with a reasonable approximation algorithm, you basically are going to need alpha to grow with the dimension in some sense. So these sets that you can approximate well are going to be ones whose entropy does not grow extremely quickly with the dimension. Okay. Now, if we look at this approximation rate we've achieved for this unit ball in the spectral Barron space, right? Part of our goal here was just to understand the spectral Barron space better. It turns out that this convergence rate of O of n to the minus alpha tells us that the entropy of this unit ball, so the entropy of the unit ball in spectral Barron space, goes as epsilon to the minus 1 over alpha. Okay, so the rate we've obtained, this minus 1/2 minus S over D, right, in L2, minus S over D, tells us that the entropy of the spectral Barron space basically goes as epsilon to the minus 2D over D plus 2S. Okay, so you can see as the smoothness parameter increases, indeed the entropy decreases. But even if S is equal to 0, so even if we look at the 0th order spectral Barron space, the entropy is still just epsilon to the minus 2. So the entropy is bounded by has a dimension independent upper bound. And this explains why you can approximate these functions well, even in high dimension. It's because the entropy isn't that large, right? But you can see still as S increases, the entropy of this set decreases, and that explains why you can get a faster approximation rate as S increases. Okay. In fact, we can also prove this lower bound. We can show that the entropy of this unit ball is in fact bounded below by epsilon to the minus 2D over D plus 2S, right? There are some logarithmic factors, so logarithmic and epsilon that I'm ignoring here, but nonetheless, what this does is this shows that this rate that we attain, minus 1/2 minus S over D, is optimal. Okay, and the point is that we've done this by essentially calculating the entropy of the spectral Barron space. All right, so, and I'd like to sort of conclude here by saying that the reason why we can approximate these functions with such a high rate is because the entropy of this set is small. And in a sense, Ron DeVore also alluded to this in his talk, is in order to overcome the curse of dimensionality, what we essentially have to do is we have to find sets with low entropy which still contain the whatever phenomenon we're interested in, contain the ground truth in a sense. And I'll also mention, so we haven't quite completed this work, which is why I'm not talking about it in this talk, but we also managed to calculate the entropy of the more general Barron space that Professor talked about yesterday as well. So that'll be some forthcoming work. Okay. So next, let's discuss these ReLU to the K networks. And the question here is, well, we saw in the previous section, we determined what the entropy of the spectral Barron space is. And this basically means we got an upper bound on how well any sort of stable method is going to be able to approximate space, approximate functions in this space. Right, so we got an upper bound in a sense on the best possible approximation rate you can have for the spectral Barron space by calculating its entropy. And now the question is, can ReLU to the K networks achieve that rate or at least come close? Because we know what the optimal sort of target rate is. How close can ReLU to the K networks, shallow ReLU to the K networks, come to that? And that's really the result that surprised us, is that they can come quite close. So let me explain how this works. So how can you use this result for cosine networks to obtain high order approximation by ReLU to the K networks? The answer is that we're basically going to start with the same decomposition we had here, right? Recall we can write our functions f as a convex combination of frequencies that lie on a lattice, right? So I'm going to start with this decomposition that we had before, and I'm going to approximate each of these complex exponentials by splines, essentially. And I'm going to do this in a multi-scale way. All right. So here I've got a plot of the B-spline N1, right? If you know what these are, that's fine. That's great, but it's not really necessary. The idea is just that we're going to take a multi-scale spline approximation of these complex exponentials. Okay, what do I mean by a multi-scale approximation? Well, the algorithm is the following. We start our initial approximation is 0, and our initial residual is f. And in each step, what we do is we take the existing error, the existing residual, project it onto a spline space with nodes that are spaced 2 to the minus L, and then add that back to to the current function f to get our next approximation. And the important thing about this is that the norms of these residuals actually decay very quickly for as long as your function is smooth enough, which the complex exponential certainly is. So they decay as 2 to the minus k plus 1 times L, where k is the degree of this ReLU. Okay, and to explain this better, here's a picture of how this would work in the case where k is equal to 1. Right, so you've got your sine function here. The initial approximation would be 0, right? And then the next level you'd take this hat, right? And in the next level you'd take, this finer hat here, right? This finer piecewise linear approximation. And ultimately this gives you an expansion of this complex exponential in terms of these B-splines, in terms of shifted and dilated B-splines. And the important thing is, if you look at these coefficients, they decay very rapidly in L. These coefficients C decay as 2 to the minus k plus 1 L. Okay, so we take this expansion of our complex exponential and put that into our previous decomposition of the function f. Okay, and now we notice a couple of things. So first of all, because the domain on which we're approximating f is bounded, this innermost sum is actually finite, and the number of terms is going to scale exactly as we know exactly how the number of terms scales. In addition, these coefficients decay very rapidly in L, and also very rapidly in the frequency C, right? This is because our function is in the spectral Barron space. Putting all of this stuff together and using a stratified sampling argument, which is similar to what Barron did, it turns out that you can obtain the following theorem. Okay, so this looks like a bit of a mess, but let me briefly elucidate this. So it turns out that what's going on here is we're trying to approximate f that are in the spectral Barron space. Here we need to now assume that s is at least 1/2, and we get the rate n to the minus t up to some logarithmic terms. I've got a graph that kind of explains, and the value of the rate here, t, is given by this expression. Okay, and the value of the logarithm, the exponent on the logarithm, is given by this expression. So I've got a graph that I think helps elucidate this. So this is in L2 for m, so for m is equal to 0. If your smoothness is 1/2, you get the rate n to the minus 1/2. Now, as you increase s, right, as you make your function smoother and smoother, the rate increases with a slope of 1/d plus 1, right? And it does this up to the limit value of k plus 1. So this is the maximal rate you can attain, it turns out. Once you hit this, the rate no longer increases with increasing smoothness. And we summarize this as a separate theorem, right? So for sufficiently smooth functions, we can obtain this rate of approximation for ReLU to the k networks, right? And it turns out, right, we're only using polynomials of degree k. We don't even need deep networks for this, right? So it turns out that this spectral Barron space is simple enough in a sense that ReLU to the k networks can approximate them functions in this class very, very accurately with a very high rate, and that's essentially what we've shown, right? So the spectral Barron space is simple enough that ReLU to the k networks can approximate it remarkably well, much better than any other traditional methods would. Okay. Finally, let me also mention this is an optimal rate. You can do this by essentially reducing to the 1D case, and let me conclude here. There are a lot of additional questions and interesting problems to consider. In particular, we need to be able to find a way to solve the corresponding optimization problems, and also, it's not clear that this spectral Barron space is really the right space. So there are many open problems. Thanks for your attention, and I'll take questions at this point.
All right. Thank you very much for excellent talk, John. And now floor is open for questions.
There's nothing in the chat right now, but I have a few questions. So first, would you say that this is part of your result essentially that the Barron spaces were sort of inspired by what those standard sort of one layer, neural networks could construct? Is this kind of also a statement on the simplicity of Barron spaces, or is that not a fair characteristic?
Yeah, in a sense it is. I would say, right, if you look back here, what we essentially, part of what we've done is we've determined the entropy of these Barron spaces. So these Barron spaces have surprisingly low entropy. So they're quite simple, which means you can attain these high approximation rates. But what's kind of not, the other part of it is that actually it's not clear that ReLU to the K networks will actually attain these rates, if that makes sense. It seems sort of more plausible because they're sort of defined in terms of the Fourier transform. It seems more plausible that cosine networks would be able to attain sort of these best possible rates, but it's somewhat surprising, at least it was to us, that these ReLU to the K networks would also be able to get quite close to the sort of best possible rate you could get for these Barron spaces. But yeah, part of it is the fact that, yeah, these spaces have very low entropy, and they are fairly simple. Yeah.
What is this? Maybe this is a dumb question, but what could you say about like an activation function that was had compact support? Is that trivial in some sense? Does that reduce back to finite elements somehow, or?
Well, so I guess one thing I'll say about it is, so first of all, when we represent things by ReLU to the K networks, we're actually using compactly supported functions, right? We're actually using these B-splines, which are compactly supported. But it depends on the statement that you're interested in, right? If you're interested in a statement like this holds for all compactly supported activation functions, the best we've been able to find is, let me go back here. The best we've been able to find is essentially this result here. So if you want to make very minimal assumptions on the activation function, it's quite difficult to come up with good rates, right? Because assumptions on the activation function are very weak.
Let's see, there's something in the chat here. How do you compare your results of Uratsky's ReLU sign network for C to the S functions with S greater than 0? His approximation rate is dimension independent.
Right. So, so Uratsky's results, if I understand them correctly, they apply right to these Lipschitz spaces CS. So they don't have to do with the Barron space, and these spaces in high dimensions do have very high entropy. But the way I understand it is that by using these two activation functions, you dramatically enlarge the space of possible neural networks in a way that allows you to overcome the fact that you're approximating a huge class of functions, if that makes sense. One of the things we're interested in doing next is trying to understand how to extend this to deeper networks. And I think one of the important questions is, what is the right space of functions to try to approximate? It can't really be CS because that's too big in high dimensions, but it should be something like something else.
So using two activation functions, how do they come? I'm not familiar with Uratsky's results. How do they combine the two activation functions?
Well, so what they do is each time you have a neuron, like you can pick either one of the activation functions, if that makes sense.
Okay.
So they construct the network using two activation functions. So sort of the space of possible neural networks, if you have a layer with n, there's like 2 to the n possible ways of arranging the activation functions in each of those layers. If that makes sense.
Okay. And that gets you to see the S functions, huh?
Yeah.
Wow.
So Jonathan, very nice talk. Can I ask something here? How many? You don't have. This is how many layers? One layer. Relative to the K, but one layer.
One hidden layer, yeah.
Okay. That okay. Then I understand something. Okay. It's very nice result. I really like it. So.
Thanks.
Some of the panelists, I think, had questions if they want to unmute and ask, or I can read them from the chat. John Harlem was asking, I recalled that in the original paper of Barron, although the rate in terms of n can be independent of d, the constant can sometimes depend on d. Is that true?
Right. Yeah. So to be fair, you know, the constants, the implied constants in our results do depend on the dimension, and they depend, but they depend at most exponentially. So at most there's something like some constant to the power of the dimension. But yeah, so the constants do depend in a potentially bad way on the dimension.
Okay.
Okay. Sorry, I just, you know, got booed out from the host, so now I cannot even show my video. But my internet is so bad. But can I follow up with one little thing here, so that I understand this clear? So this is the approximation, right? Usually in the approximation, this is.
I lost him.
Like that, right? So you haven't compared it with the estimation, right? So you see what I'm saying? Like in statistics, usually there's a bias and variance. So this is what you're talking about. It's just sort of the bias term, right?
Right. Right.
Okay.
Yeah.
Good.
Sure.
And Jean Chow was asking about if you could give some more details on the lower bound, I think for the Barron spaces.
You flash the slides like a,
Yeah. I was sorry. I was
just explain that you still seem to have some time.
Yeah. Let me go back and.
The lower bound is critically important.
Yeah. So the issue is essentially what we can show is that you can't push the approximation rate beyond this k+1, right? No matter, as you increase the smoothness, you increase the approximation rate, but once you hit this limit, you can't increase it any further. So we can show that by basically by considering 1D functions and considering the question, well, how accurately can a one-dimensional function be approximated by piecewise polynomials with, say, n different pieces? It turns out that this problem has been solved, actually, and if f is not itself a piecewise polynomial, then the best rate you could possibly get is basically n to the minus k+1 if you're looking at L2, or n to the m minus k+1 in Hn. And we can leverage that basically by just observing that if I take a single frequency, right, in one of the coordinate directions, then when I approximate this function by a ReLU to the k network, then in each slice, right, if I fix all of the other coordinates, x2 through xd, then in each slice I'm approximating f by a piecewise polynomial function which has at most n breakpoints, right? And so basically in each slice, the best rate I could possibly get is this rate 26, and by integrating that, you can show that this n to the minus k+1 can't be improved. Can't be improved upon, no matter how much smoothness you have. Yeah. Yeah, so any other questions or?
So
Go ahead.
the Kolmogorov entropy is also going to be pretty small for ReLU to the k, which you did not have to explain here. But anyway, so this ReLU to the k's power, indeed, the Kolmogorov entropy is also independent of dimension.
Right, for the sort of more general Barron space, it is as well.
So if oftentimes you don't, I mean, obviously, you know, in these kind of machine learning applications, often people don't really know what the regularity of the function they're trying to learn is. So would this be kind of a method to probe that by sort of turning up K on your ReLU K network until you sort of saturated and weren't able to get better approximations?
Yeah, I mean, yeah. So what I mean, one thing you could do is in this. Yeah, so if you look at the original sort of problem, how you're approximating things, right? You've got n terms in this expansion, right? So you look at some function fn of this form, right? And I try to approximate by a function with n terms. What you can do is you can increase n, and you can look at what happens to these coefficients. As you increase n, what should happen is that eventually these coefficients become kind of bounded in L1 norm, if that makes sense, right? So the sums of the absolute values of the AI don't increase beyond a certain point. And that's kind of going to be the norm of your, would sort of be the norm of your ground truth in Barron norm, in a sense. So what you can do is, it's like getting a posterior estimate or something, right? You basically try to solve your problem, use your optimization algorithm, and then increase n. And if you observe that these coefficients AI become bounded in L1 norm, then you can kind of conclude that your ground truth has that bound in the Barron space. If that makes sense.
But I mean, well, does that reveal the regularity of the function though? Like, I was kind of thinking, because your ReLU K networks, they have this sort of increase, you know, that you were showing in your plot, where they sort of increase and then they saturate when you get to K, right? So that's assuming that you have like that much regularity in your function that you're learning, right?
Right. So
if the function is actually less regular than K, then it'll actually.
Yeah, so I guess I think if you really want to know the regularity, the best thing to do would be to look at these cosine networks, because they're kind of designed to, they're sort of designed for the spectral Barron space. So if you look at the rates for cosine networks, right, you get this S over D here. So what you could do, right, is you could try to approximate your function and see what this rate is, and from that you could try to infer S, for example. And you could also try to infer S from the norms of the coefficients of these different frequencies as well. So that would probably, if you're really interested in like how big is this in the spectral Barron space, that's what I think you should do.
So how, like, as a practical matter, I mean, what's the K that people should be thinking about? I mean, should we be thinking of K as a tuning parameter, or?
Right. So I would say it depends on what you're trying to do. I guess the application we're most interested in basically is solving PDEs. So if you're solving a PDE, your value of K is generally going to be determined by what the degree of the equation is, right? If you have derivatives to a certain order, you need K to be a certain value.
So there you can use the regularity problem to help you. I see.
Yeah.
Let's see, there's a good question in the chat here. We've got 1 minute. What is known about the stability of the approximation error with respect to variation of the neural network parameters? Could a small optimization error in the neural network parameters lead to a much increased approximation error, especially in high dimensions?
Yeah, so that's a good question. So especially with these like Barron type results, one of the interesting things is that you, when you construct your approximation, the coefficients are bounded in L1 norm. So you're basically approximating your function by essentially a convex combination of terms, and that should be fairly stable. So yeah, and that's why basically that's why the Kolmogorov entropy lower bounds your rates, is because you're kind of approximated by a convex combination of things. Yeah, I don't know if that answers the question, but.
No, I think that was good, and I think we're out of time. So thank you very much, Jonathan.
Sure.